Alright, so in this video, we're going to be looking at the squeeze theorem. The squeeze theorem. And this squeeze theorem, it's also known, my pen seems to be giving me some trouble today. Squeeze theorem, this is also known as the sandwich theorem. Sandwich theorem. And it's also known, you can also call it the pinch theorem, or the pinching theorem, right? So all of these are referring to the same thing here. And so in order to understand exactly what this is, let's look at a relationship between some three functions here. So let's say we have a function g of x, f of x, and h of x. So we're going to have a function g of x, f of x, and h of x. So what this here is saying is that our function f of x is in between g of x and h of x. So it could be equal to g of x or it could be equal to h of x, but the main thing here is that it is in between these two functions. So if we were to graph this out, then again g of x would always be, the lower bound, or would be underneath, and on top would be h of x, and in between these two functions would be f of x. So this is sort of the thing that we've established here between these three functions. Now let's say that we want to try to find some limits here. So if we were starting to find the limit as x approaches some value a here of our function g of x, for instance, firstly, and we get that this limit, we say that it's equal to L. It's equal to some L. And now if we also, and if we take the limit as our x approaches again that same a for our h of x, and this as well is equal to that same value of L, then we can say that this limit as x approaches a of our function f of x, well, then it must also be equal to L. And we can say this again, right, because we know that our function f of x is sandwiched, right, as the name would suggest, that it's sandwiched between these functions g of x and h of x. And so if the limit as x approaches a of these two functions are the same value, then the one sandwiched in between must also be equal to it, right? So again, the key idea here is if one function is, always trapped between these two other functions, and these two outer functions g of x and h of x have the same limit, then the one that's in the middle must also have that limit too. So this is the basic idea behind the squeeze theorem, or sandwich theorem, or pinching theorem. And so conceptually, it is not too difficult to understand, right? It makes sense logically. If you have something in between these two limits, and the outer limits have the same value, then the inner one must as well. So let's just now look at an example problem in order to see how we can execute this, or how we can use this fact to our advantage in order to solve some tricky limits. Alright, so let's say this is the limit that we're trying to find. The limit as x approaches 0 of x squared times cosine of 1 over x squared. So this is something that clearly we can't use direct substitution for, but we can use the sandwich theorem. So this looks very complicated, but for a moment, if we kind of get rid of everything else and just look at the cosine part, so if we see that we have the cosine of 1 over x squared, what is something that we can figure out, or what is something that we can say about this function? Well, we know that this function is always going to be bound between -1 and 1. And the reason we know this is because it's a cosine function. It is a cosine function. It is going to be constantly oscillating between the same two values, right? It's always going to be either on the upper bound 1 or on the lower bound -1. And so we're always going to be bound between these two values for a cosine function. And so again, it doesn't matter exactly what this specific cosine function looks like. This is cosine of 1 over x squared. It doesn't matter because any cosine is always going to be between -1 and 1. And so now if we want to start to introduce the rest of our function in here, let's bring in that x squared. So if we multiply our cosine of 1 over x squared by x squared in order to get our original function, right, we now get x squared times cosine of 1 over x squared. And now, with all of our experience with algebra, can we say that, or can we simply multiply one thing by a certain number or a certain variable and leave the rest as is? Obviously not, right? Now that means we have to multiply the -1 and the 1 by x squared as well. So that would give us negative x squared and positive x squared. So now, if we want to then, how can we use this in order to find our limit, right? Our original limit. Well, this is looking very similar to something that we saw previously with our squeeze theorem. The g of x and h of x, and sandwiched in between is our f of x. So that means if we can find the limits of these lower and upper functions, then we know, and again, if those two functions had the same limit, then we can say that the thing in between, this thing sandwiched in between, also has the same limit. So then we can write this out as the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of x squared times cosine of 1 over x squared. Again, it's just a lot of writing. And then this is sandwiched in between, again, the limit as x approaches 0 of positive x squared. And so to find our outer and inner limit, or the two outer limits here, we can simply use direct substitution, right? The limit as x approaches 0 of negative x squared. This is direct substitution, and we can say that it's 0. And then if we just rewrite our inner function here again, and this is all work that is kind of necessary to be shown on an exam in order to get credit, whether it's the AP exam or an exam in your university. It's very likely that you're going to have to show this work just so you see how we're getting this answer, and it's proof of this theorem. And we can again use direct substitution here and get 0. And so we can see that sandwiched in between two zeros here is our function. And this tells us, according to the sandwich theorem, we can say then that our limit as x approaches 0 of x squared times cosine of 1 over x squared must also equal to 0. So this is our answer and how we can use the squeeze theorem. So it isn't something that is too complicated here, but it is clearly a very useful tool to help us find the limits of these seemingly complex functions. So now let's look at some other examples. All right, this is a very common type of problem that you can expect to see on the AP exam as well as in a college calculus exam. And so in this problem, we're told that let g and h be the functions defined by g of x is equal to negative x squared plus 3x minus 2, and h of x is equal to 2x plus 4. And so if f is a function that satisfies g of x is less than or equal to f of x, which is less than or equal to h of x for all values of x, what is the limit as x approaches 1 of f of x? So this problem is clearly alluding to the squeeze theorem. And so here, despite not being explicitly given the function f of x, right, the expression for this function, we can still figure out its limit. And that's because of the squeeze theorem, right? The squeeze theorem tells us that, as in this case, our function f of x is sandwiched between two functions g of x and h of x. And if the values of the limits for both g of x and h of x are equal, then the limit of f of x would also equal that same value. So here we're given the explicit expressions for g of x and the function h of x. So we can find their limits, and if they happen to be equal, then we can say that by the squeeze theorem, that f of x's limit is also equal to that. So we can start by finding the limit as x approaches 1 of g of x. So specifically, our g of x here is given to be negative x squared plus 3x minus 2. So here, because this is again a continuous function, we can clearly just use direct substitution. So this is going to be equal to negative 1 squared plus 3 times 1 minus 2. This is going to be negative 1 plus 3 minus 2. And now we can see that this is going to give us a value of 0. So the limit of as x approaches 1 of g of x is going to be equal to 0. So now we can try to find the limit of h of x. So the limit as x approaches 1 of h of x, which here is 2x plus 4. So give this a shot yourself. Again, clearly we can use direct substitution for this problem as well, or for this function as well. So we can just do 2 times 1 plus 4. So this is equal to 6. So the limit as x approaches 1 of our function h of x is equal to 6. So here we can see that our g of x and our h of x are not equal. And so if we were to write this out, we can say again 0 is less than or equal to the limit as x approaches 1 of our f of x, and this is between 6 as well. So in this case, we cannot use the squeeze theorem. And so here we cannot determine the limit. So now let's look at another problem. All right, in this problem, we're told that g of x is equal to the cosine of pi over 3 times x plus 1, and h of x is equal to x squared plus 2. If f of x satisfies g of x is less than or equal to f of x, which is less than or equal to h of x, for negative 2, which is less, for the value is negative 2 between, is less than or equal to x, which is less than or equal to 2, what is the limit as x approaches 0 of f of x? So if you want to take a minute and pause the video and approach this problem as we have done with the previous problems, then give it a shot. All right. So assume that you have given your own attempt at this problem, or approach this problem in a way that we have been approaching the past few problems, and you should see that for this problem, again, much like what we've seen, is that, again, they're alluding to the sandwich theorem here. And so we simply have to find the limits of these outer functions, g of x and h of x, and if they are equal to one another, then we have found the limit of f of x. So here, this negative 2, this constraint here is really just there to distract you or to confuse you. It actually doesn't really serve any purpose in this problem. So do not get confused by this value, which is again a common misdirect in the AP exam. So here we can again try to find the limit as x approaches 0 of our g of x, in this case the cosine of pi over 3 times x plus 1. That's plus 1. So here, again, we can try to employ our direct substitution, and we can see that if we plug in 0 here to our cosine function, we're going to get pi times 3 times 0, which is 0. Sorry, pi over 3 times 0, which is 0. Cosine of 0 is 1. And so 1 plus 1 is going to be equal to 2. So that is going to be the answer to our limit. Over here, we can just use direct substitution. So now if we wanted to find the limit for our h of x, we would see that our h of x here is x squared plus 2. Once again, we can use direct substitution, and we see that 0 squared plus 2 is going to simply be equal to 2. So in this case, unlike in the last problem, we can see here that the limit of our outer functions, g of x and h of x, are actually equal. They both equal 2. And so because of this, by the squeeze theorem, we can say that the limit as x approaches 0 of our f of x, again, despite not being explicitly stated the exact value of this function, we can still say that this function's limit is going to be equal to 2. So hopefully that's making some sense. Again, once you have the concept down, it's quite clear, it's quite easy to identify problems where you have to use the squeeze theorem, as they're kind of even set up in this sort of way. So that brings us to the end of this video. The key steps, again, or closing line here for this squeeze theorem is, firstly, again, just identify the bounding functions here. Take the limits of each of those as x approaches the point. And if they match, you've sort of squeezed your f of x to that value. And so that's how you're going to use your squeeze theorem. So if you found this video helpful, please show your support by liking and subscribing. And, leave in the comments what you'd like to see next and any questions that you may have. And I'll see you in the next video.